DARPA wants to reinvent the physics of bunker-busting weapons. The United States just used its most powerful conventional bombs against the deepest underground nuclear facility in the world those bombs worked. And they also revealed exactly where current physics ends, and the next weapons problem begins. DARPA is now looking for solutions to that problem. The Defense Advanced Research Projects Agency, the Pentagon's research arm responsible for developing technologies that define the next generation of American military capability, published a request for information on May 27, seeking what it calls disruptive approaches to penetration mechanics and shock propagation control. The document describes a program aimed at moving beyond everything current bunker-busting munitions can do, targeting the fundamental physics of how objects penetrate hardened materials and how explosive shockwaves travel through solid structures. Responses are due June 26, 2026. On June 22, 2025, 7B-2 Spirit stealth bombers delivered 14 GBU-57 massive ordnance penetrator bombs, the largest conventional bomb in the American arsenal, at 30,000 pounds against Iran's Fordow uranium enrichment facility, buried 80 to 90 meters beneath a mountain near the city of Qom. The GBU-57, which was specifically developed to destroy facilities like Fordow, can penetrate approximately 60 meters of reinforced concrete or rock. Multiple strikes can increase that effective depth. The Fordow strikes, part of Operation Midnight Hammer, were among the most technically demanding precision strike operations in American history, and they revealed the outer edge of what existing penetrator technology can achieve against hardened targets. Satellite imagery and open-source intelligence through May 2026 shows that Iran, responding to the strikes, has been excavating new facilities to depths of 80 to 100 meters under hard granite, potentially deeper than Fordow, and potentially beyond the reliable reach of existing bunker-busting munitions. The same report notes the program appears intended to house a new generation of centrifuges. The adversary's countermove to the GBU-57 is simply to dig deeper and use harder rock, and the physics that govern how a 30,000-pound steel penetrator behaves when it hits granite at high velocity have not changed since the bomb was designed. DARPA's RFI addresses that physics problem directly and at a fundamental level. The document asks for ideas that go beyond what it calls traditional mass velocity scaling and empirical design, the current engineering paradigm in which penetrators are made heavier and faster to dig deeper. Instead, DARPA wants approaches that deliberately shape, steer, amplify, or suppress stress waves within materials that manipulate the material state of what a penetrator is passing through under extreme loading conditions, and that treat the shockwave generated by penetration as a design variable to be engineered rather than a physical consequence to be endured. To understand what that means in practical terms, some background on penetration physics is necessary. When a hardened steel penetrator strikes reinforced concrete or rock at high velocity, two things happen simultaneously. The penetrator physically displaces material as it moves forward, and the impact generates a shockwave that radiates outward through the surrounding structure. Current penetrator design optimizes the first process using geometry, material hardness, and velocity to maximize forward displacement. The shockwave, by contrast, is largely treated as a byproduct, carrying energy away from the penetration channel in ways that current designs do not actively control. What DARPA is describing is a fundamentally different paradigm, one in which the shockwave itself becomes a weapon. If the stress waves generated by penetration could be steered and amplified at a specific depth within the target structure, the effective damage could reach far beyond the physical penetration depth of the weapon body. Alternatively, controlling how failure initiates and propagates within hardened material could allow a smaller, lighter penetrator to achieve damage previously requiring a much larger weapon. The RFI specifically mentions controlled failure initiation and progression, and the coupling of structural, material, and geometric effects to achieve step-change performance against complex targets as areas of explicit interest. The Air Force awarded Applied Research Associates a 24-month contract in 2025 to develop prototype hardware for the next-generation penetrator, a program intended to replace the GBU-57 and designed to strike hardened bunkers, tunnels, and deeply buried targets. The Air Force requested $74 million in its fiscal 2026 budget to continue research, ground subscale testing, and full-scale static tests for the program. The NGP program and the DARPA RFI are parallel tracks addressing the same operational problem. One focused on near-term hardware development, and one on the longer-range science that might make a fundamentally different kind of weapon possible. The DARPA document also asks for enabling technologies that could support the underlying research, including architected or actively tunable materials, meaning materials whose internal structure can be designed or modified to interact with shockwaves in specific ways, and advanced diagnostics capable of resolving high strain rate phenomena in situ, meaning measurement tools that can observe what actually happens inside a material in the microseconds during and after a high-velocity impact. Both of these categories reflect a broader problem in penetration research. The events of interest happen so fast in such extreme conditions that they are very difficult to measure accurately, and designs have historically been validated by testing rather than by a full physical understanding of the mechanisms involved. Iran is digging deeper, and China has been building hardened underground facilities for military command infrastructure, weapons storage, and missile basing for decades, a program known in defense planning circles as the Underground Great Wall. North Korea's nuclear program relies heavily on tunneled facilities deliberately placed beyond the reach of current American strike packages. The physics problem DARPA is trying to crack is not abstract, and the countries that motivated the question are still burrowing. What gets built in response to this RFI may determine whether the next generation of American penetrating weapons can keep pace with that.